We are going to move into geometry now, and we're going to look at some of the basic underlying notions of geometry. First, we're going to look at some definitions. A point is a one-dimensional thing, and it's considered a dot. A line is going to be a vertical or horizontal slanted diagonal line. A plane is a three-dimensional flat surface, so think like rectangular prism. And then we have other representations. Now, a line is represented with arrows on either side, above it, and notation. A point is just the letters, and sometimes we will represent a line with an italicized letter. Just like in a plane, we are going to name 3 points in the plane to name it, or we will use a Greek letter. Lines have no thickness, and they extend forever in 2 directions. So if I'm given 2 points, there's only one line I can draw through them to connect the points, and that's going to be important later. So if we have P and Q and there are any 2 points, then we can create a number line on P and Q such as there is a one-to-one correspondence with the points on that line and the number line because there's only one line. In linear notations, we name it with collinear points. So line L has points A, B, and C. They're all in a line. So we could also say points A, B, and C belong to line L. It doesn't matter how you reply to them. The idea is they're collinear, meaning they're in order on a line. And if I look at points A, B, and D, D is not on the line, so it's not going to be collinear. Linear notations can be used in a lot of different ways. Any 2 collinear points on a line can be used to name the line. A line segment is going to differ from a line in that it has a line at the top with no arrows because it doesn't go on forever, and it is named with the endpoints. So it doesn't matter what points lie between A and B. This has to be line AB or line BA because we have to use the endpoints. A ray is like a line, but it extends forever only in one direction. In a ray, we use the starting point, so that finite point A, and then we can use any point after point A. So you just have to use that origination point when you're naming a ray, and the ray has an arrow in one direction. Coplanar is a little bit different because we're thinking in 3 dimensions. So points D, E, and G are coplanar. If you look at them, they lie flat on the plane, whereas line F is above the plane. So in other words, if F is above the plane and not in the plane, then it cannot be coplanar. Same thing is true with lines. If lines lie in the plane, they're going to be coplanar. But if you look at like lines EF, line GF, line DF, those are all extending out of the plane, so they're not going to be coplanar. Skew lines would be, for example, line GF and DE. So when we're looking at skew lines, they do not intersect, and there is no plane that contains them. So if you look at DE, that lies on the plane. And if you look at GF, that goes up, and those lines will never intersect because DE is going to remain in the plane, and then GF is always going to go up forever. So concurrent lines, though, would be lines like DE, EG, and EF because they all have the E. They all have a common intersection point. So concurrent lines would be lines that go through the same point of intersection. Parallel lines are 2 lines that will never intersect and have no points in common in the same plane. There are some axioms that you have between points, lines, and planes. This lesson is really a lot of vocabulary, so the majority of what you're doing when you're listening to this lecture is processing the different definitions that I'm putting out there. So there is exactly one line that contains any 2 distinct points, meaning I can only draw one line through 2 points. If I have one point, I can draw all kinds of lines through it. But once I have that second point, I can only draw one. If 2 points lie in the plane, the line that I would draw between those 2 points is also going to be in the plane. If 2 distinct planes intersect, they would intersect on a line. So what I want you to imagine is if you take a piece of paper and you hold it above your desk, put the piece of paper where the edge is touching your desk, and you could describe the intersection of the plane that is your desk and the plane that is your sheet of paper as the line where they touch, okay? So in other words, the top of the sheet of paper is not touching your desk. Just that one side of that plane is touching the desk, which is why we say that it's a line. And there is exactly one plane that contains any three distinct non-collinear points. That means points that are not in a line. I can only have three. A line and a point that are not on the line to determine a plane. So when I'm trying to name a plane, I need 2 points to be on a line and 1 point that is not on the line. Two parallel lines determine a plane. Just like in your sheet of paper, you have two parallel lines on the left and right hand side and two on the top and the bottom. That's determining the plane that your paper is. Two intersecting lines determine a plane because once they intersect, the what's between them is formed. Here are some visuals of what we call with the plane. If I have two parallel planes, it's almost like we just have the top and the bottom of a cardboard box. If I have two planes that intersect, they're going to intersect on a line. If I'm looking at this plane, I have a line here that's parallel to my plane. That's interesting, and that can happen. Here, I have A and B, which are on a line, and I have points C and D outside of it, so it forms a plane. And then I have point P here, which lies on my plane, but I have this line that's intersecting my plane. So an angle is going to be formed by two rays, and they're going to share the same endpoint. So you want to see that as adding two rays together to form an angle. The sides of an angle are the two rays that form the side, and the vertex is going to be the shared point where they meet. Two adjacent angles are next to each other, like the house adjacent to you is the house next door. So two adjacent angles are angles that are right next to each other. When we measure angles, we look at things in terms of 360 degrees. There are 360 degrees in a circle. So when I'm trying to convert things with angles, I should know that I'm not going to be exceeding 360 degrees. A minute is a decimal value of an angle, and it's found because it's 1/60th of a degree, 60 being where minutes come from. A second is 1/60th of a minute. So when we start getting angle measures where it's like 2.35 degrees, we don't typically write 0.35. So in degree measurement, we don't like to have decimals. We convert what's in those decimals into minutes and seconds. And we also have a protractor, which most of your students are going to have no idea what it is because we've moved away from using that very sadly in many classrooms. So here are some examples. If I'm looking at BAC, that would be from the top of the flagpole to the intersection A to the top of the school. The angle letter in the middle is telling you where the vertex is. That is 47 degrees and 45 minutes. So that's not 47.45. That's 47 and 45 over 60 because that's minutes. And then the measure of angle 2 is going to be 29 degrees and 58 minutes, or 58 over 60. So if I want to find BAC and I know the measure of angle 1 and angle 2, if I subtract angle 2 from angle 1, I will get my answer. So when I do the subtraction, I get 17 degrees and 47 minutes. And I'm going to have to borrow a degree. That's where that 47 came from. If I want to express 47 degrees, 45 minutes, and 36 seconds as degrees, I'm going to do 47 plus 45 over 60 plus 36 over 3600. That's where I get the decimals from there, is by doing that. Some calculators will do that conversion for you, but it often gets more tricky than it's worth to use a calculator. An acute angle is an angle that's less than 90 degrees, and a right angle is exactly 90 degrees. An obtuse angle is greater than 90, but less than 180. A lot of people miss that. And a straight angle is exactly 180 degrees. If I'm dealing with a circle, we use a lot of information with circles in geometry. So in a circle, we actually call this as the set of all points in a plane that are the same distance, i.e. radius, from a given point, which is the center. An arc is a part of that circle that can be drawn without lifting a pencil. And it's shown with the arc, the little U there over CD. A chord is any segment that has an endpoint on the circle. It has to have both endpoints on the circle. A diameter goes through the center and has endpoints on the circle. A minor arc is one that's found by some central angle and whose measure is less than 180. So think about a minor arc kind of like an acute angle. A minor arc is less than 180 degrees, so it's less than the majority of the circle. A major arc is determined by what we call a reflex angle, whose measure is greater than 180 degrees. And when I'm looking at the context there, a central angle and its arc have the same degree measure. So let's say that COB was 60 degrees, then the arc BC is also 60 degrees. An arc determined by a diameter is called a semicircle because it divides a circle in half. So AD would be a semicircle. A semicircle of circle O is also considered to have the center O. So here's an example. If I want to find the measure of arc AB with its associated central angle AOB, then I'm going to look at my measurement as I have 180 degrees, and I know that arc here from FA is 60. So if I take 60 away from that 120, that'll tell me the rest of AB because that is a semicircle from F to B. If I want to find the measure of arc AF with that central angle, the measure of the arc is equal to the measure of the central angle. And a central angle has to go through the center of the circle. If I want to find the measure of arc BC that's associated with the central angle BOC, I know that BOC is 60 degrees because these are vertical angles. Vertical angles are angles that are directly across from one another in an X. So if you look at that, it forms an X here from A to O and B to F. So I have that X so that I know that's also going to be 60. If I want to find the measure of arc FDC, once again, if I'm looking at FDC, I know that FCB is a semicircle. I know from that information that I have an arc of 60 degrees here. So I know I'm going to take away 60 degrees because I know that BC is 60, and that's going to give me the 120. Two perpendicular lines are lines that meet at a 90-degree angle, and we use that T to show that two things are perpendicular. A line that is perpendicular to a plane is it intersects with the plane. And if you think about a sheet of paper, no matter what you try and do with the line that comes out of it, it kind of winds up almost looking like it's almost always 90 degrees. Even when you're shifting your pencil, the plane kind of moves a little bit, and you kind of get this interesting situation with perpendiculars when you've got a line in a plane. Two planes are perpendicular if they meet at a right angle. So if you took two sheets of paper and you put them together at a 90-degree angle, they would be perpendicular planes. Dihedral angles are formed by the union of two half planes, and they have right angles with the half planes.